Welcome to my new calculus channel. My name is John Gabriel, and today I'm going to continue with the 6th lecture in this series covering my ebook on the single variable introduction to the new calculus. A link to the free ebook will be available once again in the details section, and also links to other relevant applets or information. So let's begin. Now, we saw that in the last video, we looked at the chapter on how we got numbers, and before that, the fact that there are no axioms or postulates, and the previous 3 chapters, no mainstream misconceptions, and what it means for a concept to be well-defined, with a brief history of the most relevant events. Now, in this chapter, we're going to look at how we got algebra. And this has more interest historically than anything else, but it's vitally important because it's information that you've never seen anywhere else before, and it's refreshing from the point of view that you will acquire a very deep understanding of both geometry and algebra. So in this chapter, let's go to it. Right. The ancient Greeks actually used many equations, even though they didn't use the same symbols of modern algebra. And before I continue here, I want to divert a little bit and go to my notes. So the foundations of algebra are actually composed of 2 parts. 1, the common notions which are found in the Elements, Book 1, and 2, the arithmetic operators and the magnitude or number operations, which are available in Book 5 and Proposition 12. And in this proposition, it didn't actually touch on number at all, because all the arithmetic operations are done with magnitudes. So it doesn't matter whether the magnitude was measurable or not. All that mattered was that the operations were carefully defined using geometry. And I've covered that in the previous chapter, but I'll show you very briefly once again what it means. And then the third part is the transition from geometry to algebra. That means instead of using line segment lengths, areas through visualizations of geometry, in other words, drawing line segments, drawing the actual areas of squares and rectangles, etc., all these are replaced by numbers and or symbols. And it doesn't matter if you have an incommensurable magnitude, because you can simply write down its symbol, for example, pi or square root 2, and manipulate it exactly the same way as you would a variable in algebra. And I'll show you also how that's done. So the first part, the common notions, let's just go there quickly. These are the common notions, kine and nia. Okay, that's what it says there in the ancient Greek, and it literally means common notions. Now, these 5 common notions, I think there are only 5, if I'm not mistaken. Yes, there are 5 common notions, and they're actually the foundations of all mathematics. And they're very simple, in fact. Now, 2 of these can be condensed into 1. For example, 2 and 3 really are saying this, that if the same object is changed, if objects that are the same are changed in the same way, then the result will be the same in each case. That's what it's really saying, okay? Both of these here, 2 and 3. So ancient Greek, again, just a little diversion into the language, is quite different from modern Greek. You'll never hear a modern Greek use this expression here. And just to show you, even the Google Translate, which is obviously not designed for ancient Greek, but because there isn't a major difference in the pronunciation of modern and ancient Greek, will, in fact, be able to understand most of the pronunciation and there'll probably only be differences in the orthography or the grammar. So let me try reading this and see what it does, just for the heck of it. Oops, seems like we, right. Ta, to, αυτό. So this is quite strange. Okay, let's just start again. I think I'll have to say it more continuously. All right. Ta, to, αυτό, ίσα και αλληλείς εστιν ίσα. Okay. I put okay there. Never mind. So this is what it says. Things are equal and equal. So it's not really correct in the English, and the way that it doesn't even sound very correct in modern Greek. Okay, so literally this says here ta, it means this, which is kind of strange to have the and this following each other, and αυτό means this again. So it's this equal, and others is equal or are equal. Okay, so that's the literal translation, which doesn't make any sense whatsoever. But the meaning is correct. The translation is correct. It basically says objects which are equal to the same thing are equal to one another. That's the gist of that common notion in Greek. So, you know, the first common notion forms the basis of everything, because an object can be anything. It can be a tangible object or an intangible object, as I explained in previous lectures. And it's very easy to see that this is true, and that common notion 2, 3, 4, and 5 is true. And so let's do this. Let's go over here and let me just scratch on here, or be able to write on here. So, all right. So it doesn't matter if you have any object. So where am I here? Whoops, right over here, right? So if you have, let's say, a circle, right? And another circle which is exactly the same. Now, this is not a tangible object, it's intangible. But if we were to divide these in the same way, or take a certain portion of them in the same way, let's say we just did that and that, then obviously, and remove this portion here from each of them, then what remains, this section here and this section here, must be equal, right? That's what it's saying. That's not an axiom. You don't need to believe in that. That's proof by the very fact of symmetry, right? And if objects are equal, they're symmetrical. That's what symmetry means. It means they have the same measure. The Greek word symmetry means the same measure. If you compare them, you see no difference, okay? And if you see no difference, then they are symmetrical. Does that make sense? Okay, so that takes care of the first common notion. And these two here are saying that if these two objects are changed in the same way, whether they're divided or parts are added to them, let's say we added a part like that, which is exactly equal to both of them, then these would still be equal, okay? And they would equal the same thing. And that's what this common notion and this one says. And things coinciding with one another are equal to one another. Obviously, they're symmetrical, and if you take one and you place it over the other, if it's a tangible object or intangible, then they must be equal to one another, okay? Because they coincide exactly. And the form is equal to the other form. They're isomorphic, okay? This form is isomorphic to this form. If you have to change them in a certain way, and apply the change to both of them, the result will be still the same thing. And of course, the whole is greater than the part refers to one particular object, which is changed in any way by removing parts of it. So if I remove that part of this rectangle, then this part here is no longer equal to the rectangle. And of course, the whole part is greater than any of its parts. That's all it's saying. So all the common notions are clear, and we don't have to revert to the Zermelo-Fraenkel axioms and all the other rot that you find in set theory. Okay, so now, so how did this happen to define whatever we see in geometry and in algebra? Well, now if we go back to this page here, to this little guide, we see that the common notions are where everything begins. And then we look at the arithmetic operators, right? And the arithmetic operators are found by studying the properties of geometry. So if we, for example, had to look at this construction here, we can see that we've defined division and multiplication in terms of magnitude, right? So we know that, for example, this dark blue line is in proportion to the red line, and the black line is in proportion to the cyan line, okay, cyan-colored line. And so we always have this identity, no matter what, okay? And so that gives us division and multiplication, because obviously if we want to divide this magnitude by the blue one, then it's going to equal to 1.96 to this ratio here, 1.96 over 1.64, isn't it? Okay, right, so in subtraction in the same way with line segments basically says that we can, if we add the same thing to the same parts, it will equal to the other part too, right? To the other object that's being compared. So if we look at this line here and we subtract from this line that much, and whatever we subtracted from this line also has the same effect on this line. They're still the same object, right? So addition and subtraction are defined geometrically. Right. So we don't even have number at this stage. And this proposition here in book 5 is is the most important proposition, because it defines all the arithmetic operations in terms of similar triangles. And if you look at, I have the theory of fractions here. Is it this one? Yes. Now, this is a statement of the theorem, and you can demonstrate it by showing that no matter how much you subtract from this length here going this way or that way, that the ratios will still be equal. The proportionate ratios will be equal. And you can study this proposition on your own to see that it's true. And from this proposition, we can derive all the arithmetic binary operations, the quotient, the product, addition, subtraction, and cancellation, noting that this here is the general method, and this here refers to the similar triangle operations that we see in this demonstration. Everything is taken from here, and it's done in exactly this way, either with the plus or the minus. And of course, the plus is not the most primitive operator. The difference, or the minus, is the most primitive. And so you can have plus or minus here, or just a minus, and the results will still be the same, okay? And so what happens is, so we move from the common notions and we establish the operations. And then finally, we want to move away from working with line segments and strictly work with symbols and variables. And so now that's where algebra comes in, right? And so let's go back here to this chapter. We have now that the ancient Greeks knew of these equations here. They just didn't write it down like this. For example, they wouldn't write a plain number as height times width. They just said it's the product of two numbers, or two magnitudes rather, because numbers don't even matter here. It's just the product of two magnitudes, which is defined as I showed you over here, okay? Which is defined here. I don't need to put those numbers in there. I could just think of these in terms of magnitudes. I could call this AB to B, C, etc. They don't even have to be numbers. All this here works with magnitudes. And so these equations were known to the ancient Greeks, except that they weren't written that way. And so the equations of all the conics and many trigonometric identities were also known. So before algebra in the form that we realize it today could be realized, it was imperative that a means was possible to denote magnitudes or sizes, right? In other words, whether or not they were described by a number. And the best approach was through the use of numbers and symbols. And well, we saw how we got the perfect derivation of numbers in chapter 5, on the chapter which showed us how to derive number from scratch, right? So not this chapter here, but the one before it. I'm not going to go over it again, but you can read it, and it shows you there how to derive the concept of number. So the best approach to use algebra was through the manipulation of numbers and symbols. And symbols were required because there are magnitudes that could not be measured. For example, pi, square root 2, e, etc., right? So algebra was developed in order to communicate the ideas of geometry without having to refer to diagrams, visualizations, or instantiations, all the time. And this was the main idea, but was never fully realized because certain distances or magnitudes can only be fully understood through geometry. For example, square root 2, pi, etc. Now, all these equations that you see here are identical. And you'll notice, if you study carefully, that there's no difference between the way x, pi, and square root 2 are treated. They're all treated identically in algebra. So all those statements, these here, imply that the product of 2 and 3 is 6. Okay? Now, we also see that pi is a factor of both sides. And notice that pi is a magnitude. So a magnitude can be a factor in geometry. And this the Greeks knew long before they even knew about numbers. They knew about prime magnitudes, okay? In other words, they didn't even have to be measured. They knew about them. And it is clear that in algebra, both numbers and symbols are treated the same. Now, I've also covered this part here, and then the next big step is what we inherited from our friends, the Arabs and the Indians, zero. While very useful, we need to put zero in perspective. It's not a number, never mind a rational number. And you can see why that is the case in this chapter by reading what I have to say here. Its most important use is as a placeholder. And of course, we could do all of mathematics as the ancient Greeks did without using zero at all. So for example, if we carried around a template like this, we could represent any number we wish to represent. And we wouldn't need to use zero at all. But of course, zero is extremely useful for disambiguation. And so it's earned its place in mathematics, but it's also brought along its own baggage, right? And the baggage of zero is that we can end up having anomalies, as in this example here, where we manipulate symbols, and it seems like if we're dealing with magnitudes, we're doing everything correctly. But the fact is that there is a problem here because there is no such thing as a zero magnitude, okay? There is no such thing as a zero magnitude, and so we have a problem when we try to do this using only algebra, as a minus b is equal to 0, and so the division is not possible. And all this is in the free ebook, which you can read. Now, we can see that addition and subtraction by zero never affects an equation, right? And by the way, what is an equation? Back again to the roots, the foundations of mathematics. It says that things equal to the same things are equal to one another. What is that telling you? That's telling you the first basic rule about algebra. Whatever you do to the one side, you do to the other side, because they need to remain equal. That's why you place an equal in the middle. Otherwise, you have an inequality, right? Okay. So zero doesn't make any difference. However, multiplication and division will inevitably change the sense and value of an equation. So we'll see now what the sense and value are. And you've never heard of these terms used in algebra before. I'm the first to reveal this to you. Let's just see here how it doesn't change these operations here, the addition and subtraction. Well, if we add 0 to both sides, it's still a is equal to a. And if we subtract 0, it's still a is equal to a. But now, the problem with multiplication is that 0 equals 0 is not the same as a is equal to a, right? So the sense of the equation relates a to a. Now, if we multiply the equation both sides by 0, then it changes the value of both sides. So both the sense and the value are altered, and you no longer have the original equation that you had. Similarly, a divided by 0 is the same as a multiplied by 1 over 0, which is not a number and therefore is meaningless. Okay? So in the example where you saw an anomaly, this example here, therefore 2 is equal to 1, what happens is this. A squared is related to AB for any value. This is the sense of the equation. If the equation is manipulated incorrectly, as shown in the previous example, this relationship is destroyed. That is, 2b is equal to b, or 2a is equal to a, which is obviously nonsense, right? The value describes the size of a squared, ab, or b squared, right? So thus, while 0 is immensely useful, it brings along its own bag of snares because it does not behave as do all the numbers. How can it? It's not a number. The main idea of equations is to remember that whatever operation is performed on one side must be done to the other side. In other words, must not affect the sense, and the relationship must remain intact, which is only possible if the operation is carried out on both sides. Now, let's take a look at the magnitude E. This magnitude is really realized as the distance of the straight green line. This E is this distance here. And this function here is what we can use to derive E. And I've given you a derivation of E here without any use of calculus or limit theory, which is flawed. And it's done from scratch. And I'll show you how to find E using this method here. And so E to the x is in fact equal to the function of x comma 0, right? And ultimately, E to the 0 is equal to 1. And you can see how to derive that using the series, which you should by this time also know if you've completed a high school course in AP Calculus or A-level mathematics or IBHL mathematics. So that's pretty straightforward. Now, the gist of everything that I've told you so far is that algebra came from geometry, and the greatest contributions were already laid and set by the Greeks, okay? They had basically done everything. The Arabs and the Indians took the next step of divorcing the ideas from the actual geometry. In other words, working strictly with symbols and numbers that represent those geometrical concepts. For example, a squared doesn't really mean anything if it's not interpreted geometrically. Neither does A itself. What is A? Is it a magnitude? Is it a mass? A mass magnitude? Is it a length magnitude, an area magnitude? What is it? We don't know, right? So we tend to talk about those symbols when we work in physics by using units, either physical units or some other kind of unit. So that is the end of lecture 6, and I've shown you now how we got algebra, an interesting bit of history, and some things some new things that hopefully have given you a deeper understanding. And perhaps next time we'll be able to cover the second most important concept in mathematics, which is the arithmetic mean. This is a new calculus channel. My name is John Gabriel. Until next time, goodbye.